Jai Hind. Myself Ravindra Kumar, AP in EN Department, AKGEC Engineering College, Ghaziabad. Today I am presenting on the topic power factor improvement in the electrical circuits. So first thing we will discuss the various headings or various subtopics under this heading, that what is power factor, what are the reasons for poor power factor or low power factor, and what are the problems or disadvantages due to poor power factor, and what are the various methods in order to improve the power factor. So if we see it, these are the contents in this. So we will discuss all these various subtopics under this heading, power factor improvement. So if we go further, first is introduction part. So if we see all the AC machines like motors, transformers, they are having basically two types of powers, that is active power and reactive power. Active power, that is entirely transformed into the mechanical power or work in case of motors, and plus some heat loss that are also known as copper loss, they also take place during this transformation from electrical power to mechanical power. While this reactive power, this is used to magnetize the circuit of electrical machines and various inductive loads which are used in all the industries. So that's why the problem of poor power factor or low power factor that is occurring in the electrical power system. If we see the range of power factor, that is lying between 0 to 1. Maximum value is 1, that is the ideal case. When voltage and current they are in same phase, that time power factor is unity or 1. Otherwise power factor is less than 1, and minimum it is 0. So poor power factor, that is lying in smaller range of power factor, that is like 0.2, 0.3, 0.5, 0.6, all these are known as poor power factor. And when power factor is poor or low, there are different problems which take place that we will discuss under this. So if we go further, first we see what is the definition of power factor. So if we see it, the various definitions for this, number one, it is the ratio of kW to kVA. kW to kVA means it is the ratio of active power to apparent power. Since kW is the unit for active power and kVA is the unit for apparent power, so the ratio of these two, that is power factor. That is one of the definition. Mathematically we can represent by this formula, that power factor is which is represented by cos phi. So this is the ratio of useful power in kilowatt to the apparent power in kVA. So that is the mathematical relation as per this definition. Now another definition, if we see, it is the ratio of resistance to impedance, that is also known as power factor. So we can write power factor is cos phi, that already we have seen in the first definition. So this is the ratio of resistance in the circuit to the impedance in the circuit. So R represents the resistance and Z represents the impedance in the circuit. So the ratio of these two, that is also known as power factor. Next definition, third definition, the cosine of the angle between voltage and current, that is also known as power factor. So that means cos phi, that we are writing as power factor. So phi is the angle between voltage and current. Phi represents angle between voltage and current, and the cosine of that angle, V is for voltage and I is for current. So the angle between these two, that is phi suppose, and cosine of this angle, that is known as power factor. So these are the various definitions for power factor. Now if we go for the reason, that what are the various reasons for the poor power factor or low power factor. So if we see it, a great proportion of electrical machinery that is used in the industry, that has inherently low power factor. Why it is low? There are the reasons for this. Some equipments with low power factor, they are, as per the list we can see it, what are the equipments which are having poor power factor or low power factor. They are welding machine, then induction furnaces and electric arc, then induction motor, then fluorescent lighting and induction furnaces and choke coil. All these are the different types of equipments or machinery which are having poor power factor. So the reason behind this, why they are having poor power factor, the reason for that is, we know power factor cos phi, that is the ratio of resistance to impedance, that already we have seen in the previous slide as per the definition of power factor. So what happens in the different equipments or machinery that are listed down in this, they are having windings, and those windings are having small resistance, so that we can reduce I square R losses or copper losses or heat losses in the machine or equipment, but inductance of the winding, that is large value, and on account of that the impedance that becomes large in comparison to resistance, and so that this ratio R upon Z, that becomes a small value since R is small and Z is more. So power factor becomes a small value or poor value. So this is the basic reason that why the power factor is poor or low, and these are the various equipments or machinery which are having this problem of poor power factor. So now if next we see what are the disadvantages of poor or low power factor, or say what are the problems due to the poor power factor or low power factor. So if we see it, first is increase in the conductor size. Why it happens? We know power in the circuit, that is given by RMS voltage into RMS current into power factor. So if we see, current will be given by P upon V cos phi. Now for a given value of power to be supplied in the circuit at a given voltage, we can say current will be inversely proportional to power factor cos phi, since P and V are given. So in that case, if power factor is poor, the current passing through the line which is supplying the power in the circuit, that will become large current, and for carrying large current in the line, the size of the conductor that will increase. So due to that, this is the increase in conductor size, that is the reason behind this. Next problem, increase in copper losses, which is also known as I square R losses. So why it is so? Since current increases, so I square R losses, they are also more due to this, that is another problem due to this. Next, reduce efficiency. Why it is so? When copper losses are increased, the efficiency naturally it will reduce, since efficiency we know it is given by output upon input, and in case when losses are more, so output that will be written as input minus losses. So efficiency will be this that time, and when losses are more due to increase in current due to poor power factor, naturally efficiency will go down, so it will reduce. Next, larger kVA rating of the equipment, and hence it results in increase in cost of the equipment. Why it happens? kVA, that is a product of, basically it is volt ampere rating. When we are taking kVA rating, so this is kilovolt ampere rating. So with the increase in current at a given voltage, so naturally the product of volt into ampere that will increase. So that will result in larger kVA rating of the equipment, and that will result in the cost of the equipment increase. So this is another issue or another problem due to poor power factor. So these are the another problem we can go for poor voltage regulation. Why it happens? When current increases in the line due to poor power factor, that already we have discussed. So voltage drop also increases due to this, and due to the increase in voltage drop, the voltage variation increases, and with the increase in voltage variation, the voltage regulation becomes bad or poor. So that is another issue due to this poor power factor. Plus one more thing we can see, when we are like in first point, we have seen increase in the conductor size due to poor power factor. So it will result or it will affect the economy also, since for increase in the conductor size, the cost of the conductor will increase and it will affect the economy also. So all these are the problems or the issues due to poor power factor. So now next we have what are the various equipments which are used for improving the power factor. So we already have seen what is why the power factor is poor and what are the problems due to poor power factor. So what we are to do, we are to somehow to improve the power factor so that all such problems can be minimized or avoided. So we use various equipments for power factor improvement. So if we see it, these are static capacitor. So this is what is this? We know capacitors, they are taking leading power factor current. So it causes leading power factor. Why? Since it shifts the current ahead of the voltage by 90 degree. So in order to correct the lagging power factor, which is poor power factor also, we use capacitor for power factor improvement. So it is a convenient method for improvement of power factor. Next we have synchronous condenser. This is also a capacitor, but it is a rotating capacitor. Basically it is a synchronous motor which is rotating at synchronous speed, and we use it in overexcited region, and that times it takes leading power factor current. So it behaves like a capacitor, and that's why we call it synchronous capacitor or synchronous condenser. So if we see it, it is a synchronous motor that rotates under load condition, no load condition. A synchronous motor shows capacitive behavior while operating in overexcited mode or leading power factor mode also we call it. By controlling the field excitation, power factor can be adjusted continuously. That is the advantage associated with this, and it provides stepless power factor correction by the help of this. So basically if we compare these two methods, static capacitor and synchronous condenser, in case of static capacitor, that will be using some steps for power factor correction. That will not be just like a smooth power factor correction, but in case of synchronous condenser, it will be a stepless power factor correction that we can see. That means this will be a smooth power factor correction rather than a step in a stepped order power factor correction. So these methods, or say these equipments, they are used for power factor improvement. So next we discuss these methods, how do we improve the power factor with the help of these equipments, namely static capacitor, which is a stationary capacitor, and second one synchronous condenser, which is a rotating capacitor also we can say it. Basically it is a synchronous motor which is rotating, and when it is used in the overexcited region, that time it is behaving like a capacitor since it is taking leading power factor current, so that it is just like a capacitor and it is used for power factor improvement. So if we see it, methods for power factor improvement, the methodology which is employed to improve the power factor, that involves introduction of reactive power in the system, and that is introduced in such a manner that it is in phase opposition to the wattless or reactive current. This reactive power which is introduced in the system, that is taken just like that, it is in phase opposition to the wattless or reactive current. So due to it, what happens, the standard practice is to connect a capacitor in the power system at appropriate locations or places so as to compensate the inductive nature of the load which is already there. Since basically already we have discussed like welding machine, induction motor, they are inductive nature of load which are having poor power factor. So for improvement of those inductive nature load power factor, we are going for this method. What is happening in this, the apparent power that can be resolved in two components. One is in phase component, which this is known as active power in kilowatt or useful power in kilowatt. Any name we can give it, useful power or active power. And the second component is wattless component, which is reactive component of the power. And this is given in kVAR, which does not have any useful work in the system. So these are the two components for apparent power in the system. Now what happens? The vector sum of these two components, that is active component or useful component of power and reactive component which does not have any useful work, that is the resultant of these two is apparent power, kVA, that is the unit for this, which is drawn from the supply. Now the power factor, if we talk, for which we are talking, the cosine of the phase angle between kVA and kW, that is the power factor of the load. That already we have seen when we have seen the definitions for power factor, that it is the cosine of the angle between voltage and current, or we can also say it is the cosine of the angle between kW and kVA, where kW is useful power or active power and kVA is apparent power. So what happens further? To improve the power factor, what we have, the equipment which is drawing kVA arc, reactive power in kilovolt ampere, of approximately the same magnitude as that of the load kVA arc, that means load reactive power in kilovolt ampere reactive, but it is in phase opposition, that is leading, and this equipment that is connected in parallel with that load, for which we want to improve the power factor, and by doing so, that means by connection or by connecting this equipment which is used for power factor improvement in parallel to that load, we reduce the net reactive power, since the equipment that is taking leading reactive power while the load that is taking lagging reactive power. So these two reactive power, they are in phase opposition to each other, or 180 degree angle they are having between them, so that net reactive power is reduced, active power remains same, since this reactive component that doesn't take any active power, like capacitor that doesn't take any active power, reason being the power factor for a capacitor, pure capacitor, is 0, and the reason for that is the angle between voltage and current is 90 degree for a pure capacitor, so that power factor which is the cosine of that angle, that becomes 0. So active power remains same after connecting capacitor, but reactive power is reduced, so apparent power is also reduced, and power factor which is the ratio of active power to apparent power, that is also reduced with the help of it. We can see it in the coming slide. How do we do it? Initially we have this circuit in which one resistance and inductance, they are connected in the load. This is basically the load, the combination of resistance and inductance, and this is supplied by this AC voltage supply which is having a voltage V. The current supplied to the load, that is IL, IL is load current. So what happens if we see the figure diagram for this, we have active power which is in kilowatt kW, that is standing for kilowatt, and reactive power kVAR, kilovolt ampere reactive. So these are active power for the load and reactive power for the load, and the resultant of these two is this apparent power which is shown by dotted line, this line. So this is before connecting any capacitor with the load and the angle between active power and apparent power, which is angle phi 1, the cosine of this angle, that is power factor for the load. Now we want to improve this power factor, so what we do, we connect a capacitor in parallel to the load. So what we have, we are connecting one capacitor, this is connected in parallel to this load, this is load, this complete one is load, that already we have seen, that load is consisting of one resistance and inductance in series. So a capacitor that is connected in parallel to this load, supply voltage is same, that already we have seen in this previous circuit. So what happens now, the supply current I, it will be having two components now, one is load current IL, another one is capacitor current IC. So due to it, what will happen now, the reactive current in capacitor, that will be leading by 90 degree from the voltage, while the reactive current in the load, that is lagging by 90 degree from the voltage. Those two currents are in phasor opposition from each other. So net reactive current and net reactive power reduces due to this, active power remaining same, that already we have discussed why. So apparent power, which is the resultant of active and reactive power, that also reduces with the reduction in apparent power, so reduction in reactive power while active power is same, and power factor, which is the ratio of active power to apparent power, that improves since apparent power is reduced, active power remaining same. That we can see from the phasor diagram. This is the phasor diagram for this. Active power, that is remaining same as earlier without capacitor. Reason we know, since the capacitor doesn't take any active power due to zero power factor of the capacitor. Initial load kVAR, that is this, up to this point, from starting from here up to this point, this is there. Leading kVAR, that is added due to capacitor which is connected here, and we can see this leading kVAR and lagging kVAR, they are in phasor opposition or at 180° angle from each other. So that's why the net reactive power, that is reduced, that is this one only now after connecting capacitor. This is the resultant kVAR, which is the result of load kVAR and capacitor kVAR. Active power remaining same. So apparent power, which is the resultant of active and reactive power, that also reduces due to it. So this is the reduced apparent power now after connecting capacitor, and before connecting capacitor, this is the apparent power. So if we see now the angle in first case without capacitor, that is this angle phi 1. After connecting capacitor, the angle is phi 2 now, and phi 2 is less than phi 1. So due to it, cos phi 2 will be more than cos phi 1. Or in other words, power factor, which is the ratio of active power to apparent power, active power is same but apparent power is reduced, power factor will improve. So anyway we can see it. So that is the method. By the help of this, we can improve the power factor of the system. We will discuss it mathematically in the coming slide, that we can see power factor improvement. Resultant kVA, that is now smaller or less, and the new power factor is increased or improved, that we have already seen in the previous slide. Reason being for this, power factor is ratio of useful power or active power in kilowatt to the apparent power in kVA, that already we have discussed in the definition part of power factor. So now active power or useful power, that is remaining same after connection of capacitor, but apparent power is reduced since the net reactive power is reduced after connecting capacitor, and apparent power is the resultant of active or useful power and apparent power or reactive power. So due to it, when apparent power is reduced, useful power remaining same, naturally this ratio is improving and power factor is improving due to it. So cos phi 2, that is managed by, cos phi 2 is the new power factor now after connecting capacitor, that is managed by the magnitude of kVAR added. That means how much reactive power we are adding in the system with the help of capacitor. Then any desired power factor, that can be obtained by changing the leading kVAR. That means to say, by changing the value of capacitor, we can change the power factor as per our requirement or as per our desire. Now the mathematical equation for the calculation of the capacitor capacity, that means what should be the value of capacitance of a capacitor, or what should be the capacity of capacitor, we can find it mathematically. The reactive power QC, QC represents reactive power, that is needed to reach the desired power factor, that can be calculated as QC is given by this formula, P into 10 phi nu minus 10 phi old. P is the active power in this or useful power in watt or kilowatt. 10 phi nu means, phi nu is the new power factor angle, so tangent of that, that is 10 phi nu. Phi old, that is the old power factor angle without connecting capacitor, so 10 phi old is tangent of that angle, and QC is given by this relation, which is the reactive power which is needed for power factor correction or power factor improvement in a desired value. Now true power or active power or useful power, that is given by I square into R, where I is the current in the line and R is the resistance of the load, and P is the symbol for this true power, while the apparent power, the symbol for that is S, capital S, and it is given by V square by Z. where V is the voltage of the supply and Z is the impedance in the system. So QC, that is reactive power in volt ampere reactive, VAR, and P is the real power in watt or kilowatt. The required value of the capacitor to achieve this new power factor, that can be calculated as follows. That we can see now. How can it be calculated? The capacitor value C or capacitance of the capacitor, that is given by this relation C equal to QC upon V square into W, where this QC stands for reactive power in volt ampere reactive for the capacitor that we have seen here. This is this value QC. V is the voltage of supply, that already we have seen here, this one, and omega is the angular frequency of the supply, which is given by 2 pi f. Omega is 2 pi f. So by the help of this equation, we can calculate that how much should be the capacity or capacitance of the capacitor needed to improve the power factor to a required value or desired value, by the help of by the help of this mathematical analysis or calculations for a given load or given system.